Swayam Prabha. Digital India. Educated India.
We know what are rational numbers, that's fine. So we know what is 3 by 2, but then you wrote something called square root of 3 by 2. This was your x. Huh? So why do you think this is also a number?
What's a number?
That's exactly my question.
Then how do we know this is a number?
That is exactly my question.
We assume it's a number. If we put this in
How many will assume like that?
single point,
Huh?
we have been
To solve this equation, you told x will be equal to plus or minus square root of 3 by 2. No? We had this equation. No?
Okay, so we know 3 is a number, we know 2 is a number, we know 3 by 2 is a number. So root of 3 by 2, we can define it as that which when multiplied by itself will give us 3 by 2. So that will have to be a number.
It is not a rational number. Huh?
It's not a rational.
Of course, it needs proof, but we know it's not a rational number.
we haven't defined what a number is.
We have not defined what a number is. So when you say what is a real number, how do we answer? Natural number, okay. You have defined it.
What is a number?
Huh. You would like to have irrational people in your group? There is a problem, right? You see? Because we don't know what are they. So like you take a simpler one, x square equal to 2. So how do you know there is a number that satisfies this? Well, there is no rational number which satisfies this, right? But we would like to see that something satisfies it. We have to create some symbols like that. So again it is an extension of rational to reals. Okay? We have to again go beyond it. Make it bigger still. Our set of whatever we call large numbers have to be made larger. That is our feeling. Right? So how to make it larger? Should we just assume square root of everything is there? We can say, you want to say there is a rational number q, and we will say that this. What is its meaning? It means it is, we assume that there is a number like this, or in our set we will put a symbol like this, which symbol means what? That multiplied to itself will give us q.
So is that how we defining root of any number?
I don't know,
Multiplied by itself.
because that is our method says, right? Huh? It says that I would like to put such a symbol in my set such that when this is multiplied to itself will give me q. So multiplication I am assuming, some way I can define it, right? That has to be defined again, because multiplication of rationals only defined, multiplication of such funny things have not been defined yet. So that has to be defined, and then it is to be seen that this is equal to that q. All these are responsibilities now, right? To introduce this q, root q. Otherwise root q will have no meaning. Root 2 will have no meaning, right? Is that okay? Now let's go back to your 4th or 5th standard. Can you give an example of an irrational number? Hey, big things. Give me small things. Huh? Root 2 is an irrational number. We know it is not rational, that's why. Some other way? 0 point? 0 point?
0, and then the pattern continues.
Like this? This is an irrational number. Why? So you know that rational numbers when expressed as decimals will be either terminating or non-terminating and recurring. Some portion of it will be recurring, right? That's what. But this is neither. That's why it is irrational. So here, what is the assumption of taking a number? When you say this is an example of a number which is irrational, what is the assumption of a number? What is the idea that all my numbers are like this? Yes? Simple assumption is there. So every number looks like a decimal number. That is our idea here, right? Is that okay? We are thinking that any number you say, that is a decimal number. So in the sense you have some digits here, something like this, then there are some other digits, like this. Once you can write like this, we will call this as a number. That is the idea, right? Basic idea is that. So what about root 2? Is it really explaining root 2?
Yes, sir.
Yeah? Because you have an algorithm to find out square roots. Okay? So you write 4, 1, 4, I don't remember more. Okay. Something like this. So you can find out all the digits, nth digit in it. So that means our idea is that all decimal numbers, maybe infinite number of places are there, they are numbers. Okay? Is that fine?
Using numbers to define
Digits. We are just using digits 0 to 9. So now every natural number is written as a digit, a sequence of digits, like this one. This is a natural number. Of course, there should be plus minus sign here. Sign also, right? So if you assume like that, have you really covered all those whatever you have done till now? All natural numbers can be expressed like this? Yes?
Yes, sir.
All integers can be expressed like this?
Yes, sir.
All rational numbers can be expressed like this? Yes?
Yeah.
It can be recurring, infinite decimal, or it can be terminating. Terminating is also recurring with zeros. Right? Okay? If they are non-recurring, they will be called irrational numbers. But there is a problem, big problem. How do you define addition of two infinite decimals? Okay, ordering is not difficult, right? Ordering up to infinite decimals can be given easily, just like your dictionary. In dictionary, your words are ordered. The same way these words will be ordered. They are just words now. Instead of 26, you have only 10 letters, 0 to 9. So order them like dictionary. Okay? Ordering is not a problem. Problem is addition. How do you add them? How do you add infinite decimals? So what is your idea?
Assume a finite value for that.
Assume a finite value, then? Approximation, but how to get the decimal? Which infinite decimal is that? So what is the meaning when you say it is this infinite decimal? You gave me a pattern. Why did you give a pattern? Why not give arbitrarily randomly some digits here? Reason is, you will suppose I want to find out what is the 1000th digit here. If there is a pattern, you can find out, right? So this infinite decimal means you should tell me how to get the nth digit. If you have a scheme, I will say, well, I know the number, right? If you don't have a scheme, then how do I say what is that? 1000 digit may be 5, maybe 6, maybe 7. How do I get that? It is not a definite number, right? So when you say it is an infinite decimal, it means if I give you n, you will say what is the nth digit. That should be a scheme. You may not be able to tell me in this bath, maybe in next bath you will be able to tell me. It will take a lot of time to compute, right? We are assuming, yes, let it be, but there is a scheme to compute. Okay? Alright. So, in such a scheme, suppose I give 2 infinite decimals, then how do you add them?
So we compute the infinite.
Infinite is not a number. We don't have any number in infinity, right? In natural numbers, nowhere you will see infinity.
We need some way of computing the last number.
There is no last number.
So we can first start by adding the first decimal places.
Mm-hmm.
Then adding the first 2 decimal places, adding the first 3, see which value is approaching, taking the limit, see which value is approaching, and tell that is the sum.
How do you know it approaches something or it doesn't approach?
Sir, because the maximum value of the decimal, there's a proof that's saying that 0.999 is equal to what you treated in school. So then, according to that, the maximum value which you can add 2 decimals, pure decimals, which you can add, the maximum value will get is 2. So you know that it will be a finite answer. So it's somewhere between 0 and 2.
Yes, we know it is bounded.
Yes, sir, so you can see which value is approaching and then saying.
But how do you know which value is approaching? It may not approach anything. Still it is bounded. Understood the problem? Suppose these are the 2 decimals. Okay? Now we can add them because there are finite number only. Right? So if you add, what do you get? You are telling to add from this side. So first approximation I will do 0.8, then 0.89, then 0.89. It continues like that. How many will there? Like this. Okay? It will be like this. Fine. Now what happens? Suppose after this there are digits, and some digits are there where again there is a pattern. Suppose like this. Then what happens after this 9? There will be 3. There will be 5 next. Next will be 6. Next 9. Next 3. 5. 6. So there is a pattern also that continues, right? But instead of this, suppose this pattern is repeated. Only 9 will come, right? So instead of 9, suppose one place, this becomes 6. One place, just one place. After that again 1, 2, 3, 4, 8, 7, 6, 5. It continues like this. Now what will happen? Suppose this is coming at the 1001 place.
So it will be 9 and then 999 zeros.
Up to 1000 there will be 9, right? But when you come to 1001 approximation, there will be 0 here. All these are zeros, this becomes 0.9. Right? So that makes it difficult to define the addition itself. But there is something can be seen, that once this changes, this 9 changes, whatever you change here after that, this 9 will never change. After this, it is stabilized now. So once a change happens somewhere in a digit after this sequence, it will never change again. It may change somewhere else after that, but not that. Okay? There is some stabilizing happening. That much can be observed. But then how do we define addition? This creates a lot of problem. Right? But we have the feeling that if you go like this approximation, it will be approaching some number. It will always be nearer and nearer to a number. Right? Like this. It is approaching really 0.9, but after this, when it happens, again it will be what? 9, all these 9s. Right? So then we will say that it is approaching 0.9 and these 1000 zeros and 1 1. That will be the number. That is our feeling, right? Because all these 9s will be there, they will become 1. They are equivalent to same thing. Previous digit will become 1. Okay? This will be the addition, this will be the result. But how do we get from any two arbitrary decimals like this? If you add, you will be able to see this. There is a problem, right? This is the reason real numbers are not defined as decimals, because it is very difficult to define the addition of two decimal numbers, though they can be approximated easily, but exactly we can't define, only approximation is defined, right? But there is a way to define it, possibly. That is also tedious, not very quick. It will be very indirect again. So what we need is how to see. On the one hand, we have a problem that we want root 2 type of things to be there in our number system. It is not there in rationals. On the other hand, there are decimals. Decimals we need to have it, but there is no way of defining addition. But root 2 and other things if you have, we can assume their addition is defined. Okay? So these are the troubles. We have to go around and define what a real number is. So there is a nice way of doing it, like we have done axiomatically for the natural numbers. You say there is one function s and it does work like this, right? Similarly, we will define something until it works like this. That is our real number system. Okay? So what we do? We look at our requirements. If real number set is there or the real numbers are there, what do we do with it? That is our requirement. Okay. So what do we do with real numbers? We add, we subtract, we multiply, we divide, we take roots also. Right? All those things we should be able to do. Then it is enough for us. Fine. So what are the things we should assume on the real numbers? If a real number is there, we should be able to add them, we should be able to multiply them, okay? And these two will give rise to their inverse functions, subtraction and division. We need not keep them, provided these are well defined. And then what? We should be able to take roots, and we should have one ordering of real numbers, just like your natural numbers and rational numbers. That should be an ordering. Okay? So that ordering is required. That is, what do you mean by x less than y? Or how to work with this less than relation? What properties we need for this less than relation? This must be known. Right? Then only we can work. So this is very simple. All of us have worked with those properties. When you have two algebraic expressions, you know how to simplify them. So in simplifying, you have used all these properties, very simple properties. What are they? That x plus y should be equal to y plus x. Very basic properties. Then if you add another, in which way you add does not matter. Okay. First add these two, next add this, or first add those two, next add this, does not matter. You will get the same result. Okay. And then what? X. There is something called 0 in real numbers. Okay. So that you add to any number this 0, you will get that number. And then for every x, you will get something called minus x. When you add them, you get 0. This is required for irrationals. So similarly, we will add with real numbers. From all these things whatever we have in rationals, we are just extending it to reals, all these properties. They are not very new. Then similar properties for multiplication. Okay. Provided okay. So all these properties are there in real numbers, and there is something which is interplay of this. What is that? Okay. This property also will be required. To simplify your algebraic expression, this is also required. Right? What else? We have the order property. So order property will start with one assumption that you take any two numbers, either it is less than that, or it is equal to that, or it is greater than that. Okay. This property is there. Then anything about order? Then this property should be there. Okay. If something is to the left, again another left, then this is to the left of that. Fine. These are usual properties in rational numbers also. They are just to hold in the real numbers. Then what else? How this order behaves with our operations, plus and into. So if x is less than y, then x plus z is less than y plus z. Then similar property with respect to multiplication, how it happens. So if x is less than y and 0 is less than z, then xz is less than yz. Okay. You need positive, z to be positive, otherwise it may reverse the sign.
For the definition of multiplication, should we also add that x into 0, 0, 0
No, that will follow.
in the properties?
That will follow from this. All the other properties will follow from this, basic properties. Whatever algebraic properties you have, they will follow from all this. Cancellation laws, x plus y equal to z plus y, that will give you x equal to z. 0 is less than 1 will follow from this. So all that we have now is, we will say R is a non-empty set, R has 0 and 1, and it satisfies this. Okay. All these algebraic properties are required for us. But then rational numbers also satisfy all these properties. From there only we are formulating this. No? If all of them are rational numbers, this is satisfied, this is satisfied, this is also satisfied, everything is satisfied. Also this. So how is it different from real numbers? There is something which makes real numbers different from rationals. There is a bigger set, right? Rationals also satisfy all these things. Then this will not tell us that we have got something new. It may be that. It may be something very big, just contains q in it. That is also possible, right? So there is one more property of real numbers which really distinguishes it from the rational numbers. Huh?
Whereas the irrational number will just keep on.
Okay. No, what I am telling, all these properties are also true in rational numbers. So like that property, what you tell, right? How do we distinguish that? if you assume only these things for real numbers, how do you distinguish that property? It will not follow, because they are also irrationals, right? So you need something more.
It cannot be represented by P by Q.
If you write that, then P by Q will not be a real number. Understood? If you say that, will define only irrational numbers, not real numbers. Understood? Because that number like 2 by 3, they will not be there in reals. So they have to satisfy all these properties, something more. Right? Reals should satisfy something more. That means the set of reals. Union of both the sets. But then what is there? If it satisfies this and it is not a rational number, what is it? There can be many arbitrary things which will satisfy all these things, right? In fact, anything that satisfies these axioms or properties is called a unordered field. There are many ordered fields, infinitely many ordered fields, including Q and R. Right? Which one you would like to take?
It can be represented as root of something.
Not only root, there will be something else, like pi you are telling. That is not root of anything. Root of a rational. It is not a root of a rational. Not even nth root of a rational. Not even the zero of any polynomial. Right? So there will be trouble. So what we do? It is something we want to define, and it comes from the approximation of this your decimals. It has something to do with the approximation of the decimals. Now look at those decimals. What you told that is a bounded set. No? Suppose you take those decimals, some numbers, some two numbers I take. Now what happens? These two numbers, this is between 0 and 1. This is also between 0 and 1. Therefore, when you add them, you will be getting something between 0 and 2. Right? So this says there is a bound to it. Okay? If you take addition, that means addition of all those terminating decimals coming from it, you truncate them, get the terminating decimals. So truncate each of them, you get what are the terminating decimals here? 0.1, 0.12, 0.123, all these are truncations of that. Similarly here you have the truncation 8, 8, 5, these are all truncations. Okay? Now you add any two of them, any one of these and any one of these, add them. That will always be falling between 0 and 2. Right? Do you see what I mean? You take any one of them from this, take any one up from this, add them, it will be falling between 0 and 2. Okay? So this is a bounded set. It is a bounded set, at least it has an upper bound, 2 is an upper bound to it. Everything will be less than 2. Fine. Then when you add these two, what will happen to this addition and what will happen to these sums? Can you imagine that? Say, let us write it like this: A1, this is A2, this is A3, and so on. This is B1, this is B2, this is B3, and so on. So when you add them, what do you get? You get A1 plus B1, A1 plus B2, A1 plus B3, then A2 plus B1, A2 plus B2, A2 plus B3, all these numbers you get. This is a very big set, infinite. Okay? But this is all the numbers are bounded by 2. Okay? So you think there is a maximum of this, but we don't say maximum because there are infinitely many. Right? There is a least number which is an upper bound. 2 is an upper bound. Suppose this is sum is less than 1.9, then we will say 1.9 is an upper bound. Right? So from this there will be many which are smaller, which are bigger and so on, but there is something biggest. Okay. So how do you express that? We will say it is the least of all the upper bounds. Do you see? Suppose you take root 2. So instead of root 2, I consider this set. What is that set? You take any number x which is a rational number such that 0 is less than x and x square is less than 2. I consider all rational numbers whose squares are less than 2. Right? So this has an upper bound. What is the upper bound?
Root 2.
I don't know root 2 till now. Tell me rational number. 2. 2 is an upper bound, right? 1.5 is an upper bound. Okay. So 2 is an upper bound, but 1.5 is also an upper bound. Now you find 1.42 is an upper bound, right? Now you find 1.415 is an upper bound. I am making it smaller intentionally. All these are upper bounds of this set, right? If you square it, you will get something bigger than 2. Right? Its square will be bigger than 2 always. So it can't be in the set. But it is an upper bound to this set. Every element of this set will be smaller than this. Okay? Is that convincing or not? Every element of this set, every rational number whose square is less than 2 is smaller than this. Right? So you go on making it smaller and smaller. There will be a least one, not rational number. It is a real number, and that is equal to root 2. Do you see how it is placed?
So how will we know that this least value will be contained in our parent set a1 plus b1 and a2 plus b2?
It is not there. It may not be there. It may not be there. Like this here, it is not there, because we know it is not a rational number. Least one is root 2, but that is not a rational number. So it may not be there. But there is a least which is a real number. Right? It may not be there. They are all terminating, not even rationals. All rationals are also not there, only terminating. But we are putting all rationals here, still it is not there. Right? Do you see how it is coming? You are thinking of a set like this, and then you are adding all these things, getting another set. You know it is bounded. So if it is bounded, you have many upper bounds. Among the upper bounds there is a least one. That least one will be the sum of this. That is the way it can be defined. Right? Which one? Yeah, you look at this. So everything here is a rational number whose square is less than 2. Now you see 2 is an upper bound to this. Right? 1.5 is an upper bound to this. If you square it, it will be bigger than 2. Right? This is also an upper bound to it. Take your mobile, calculate. Its square will be bigger than 2. We know 414, that's why. Right? That's why confidently I am writing. So you look at all these upper bounds. Okay? Look at all these upper bounds. So like here, if root 2 is somewhere here, these are all here, upper bounds, all upper bounds. Then you take the least of that, that is equal to root 2. Right? That list may not be inside the set. In fact, it is not here, because root 2 is not a rational number, it is outside, but there is a list. And we feel that is a real number. Right? Nowhere we have told that is a real number till now. So we have to exactly tell this now, that there is something which is least. They are in the real numbers. Right? That is the main axiom of the real numbers, which separates reals to rationals. So what is this property? This is called LUB property. So what does it say? It says every non-empty bounded above subset of R has a least upper bound in R. Simple property. You take any non-empty subset of R, if it has an upper bound, then that has a least upper bound, and that is a real number. So this is not satisfied in the rationals, right? Because set of all that less than 2, square less than 2, this least upper bound will be root 2, but root 2 is not a rational. This is not satisfied in the rationals. This is satisfied in the reals by assumption, right? So real number system will be this, that it is any set having at least 2 elements, 0 and 1, and satisfying all these properties. That is the real number system definition. Now if you start with this, you can find out natural numbers inside it, rational numbers are inside it, because 0 is there, 1 is there, addition is there, so 2 is there, 3 is there, everything is there, right? Rational numbers are there, everything is now complete. And this is the crucial property, least upper bound property of the real numbers. So anything you do in real number systems, if it is different from something that is happening in rationals, then it will use this property, and somehow it has to be derived from it. Okay? So there is a nice property which comes out of it, that is called your Archimedean property. Archimedes told Eureka after coming from the bathtub, right? So there is something associated with his name and the bathtub. So you have a big bathtub, right? And you have a very small spoon. If you go on taking out water from the small spoon, from the full big bathtub, then sometime the bathtub will be empty. Are you confident of this? Every time it is something is reduced, finally it will be empty. That is called the Archimedean property.
Sir, so the spoon can take volumes which are less than the volume.
Whatever it is, doesn't matter. Whatever it is.
Within the volume, right?
Doesn't matter. If bigger, then a half spoon will go. Eventually it will surpass it. So what does it say? This is the Archimedean property. We will write like this. Okay. So now we are assuming negatives also, doesn't matter. Even the content has negative numbers, negative of the volume, that doesn't matter also. Just take n equal to 1, a equal to this, so a is bigger than b, if it is negative. If b is very large only, then it is meaningful, right? B is bigger than 1000 and a is less than 10 to the power minus 10. Then also you will get a natural number, so that na is bigger than b. That's all. Okay? So this property also follows from this. This is very useful property which helps. Like proving that or proving this the other one. You take any real number x, then there is one integer n, so that the x lies between n and n plus 1. No? Right? You take any real number x, it will always lie between two integers, consecutive integers. Right? So that also follows from this LUB property. Everything comes from LUB property only. That's how you define your integral value function. Unless that exists, you cannot define the integral value function. Right? So what it says, that integral value function given any x real number, there exists an integer n such that n is less than or equal to x is less than n plus 1. Okay?
Less than equal to n. Less than equal to n.
No, less than will write. This will make it unique. If you allow that, then suppose x is an integer, it could be n, it could be n plus 1. This will make it unique. Right? Keep it in one place equal to, other place less than. So this function is called the integral value function. It's written like this maybe, x. Or sometimes in your book it may be written like this. Bracket. Greatest integer less than or equal to that. See, greatest integer less than or equal to that. That exists because of this Archimedean property, and which follows from least of one. That's how. Otherwise, you can't define such a function. This property helps in proving limit of 1 by n equal to 0. How do you show? Limit of 1 by n equal to 0. Intuitively, your teacher might have told you make it n bigger and bigger, it becomes smaller and smaller. But why does it go to 0? Why not 0.1? It is also smaller, right? So because if you take 0.1, you can find one integer so that 1 by n will be bigger than, will be smaller than that 0.1. So there is something smaller, then how in the limit it will be that, right? So again you will be using this integral value function there from the definition. So almost anything you do, it will use this in real number systems. Definition of pi, right? That will also do this. But now there is no time, maybe sometime you will learn it later. Okay, we stop. Any questions? Want to take photograph? Right.
How do we define complex?
Huh? Complex numbers will be just, it is R cross R. R cross R, Cartesian product with itself. Then you define addition of complex numbers through real numbers, component wise. Then multiplication of real numbers will not be component wise. We define as if I is there, right? AC minus BD like that, comma and something else. So that will make it a field. Again, all these properties will be satisfied. But it will not have the order property. It will not have the list of row and column. It is just a field. Then you write a comma b as a plus ib as a simplification. Just Cartesian product, that's all. That's why we mapped it in the plane, no? As if it is in the plane, because R is thought of as a line, so that is a plane. Okay, see you then.